In this video, I will discuss a little bit the difference between the instantaneous and the average velocity. We know by definition that the velocity in the x direction in one dimension is equal to the displacement in x, delta x, divided by the change in time. Now, there are two different limiting cases that we can use this expression. We can use it when delta t is small compared to the duration of the phenomenon we're studying. So this is case 1. And the second case is when delta t is relatively large for the duration of the phenomenon. Now let me give you one example of what this means. Let's say that I have the 0 right here, and I have my x-axis pointing to the right. Now, if I have at t equals 0, I have an object starting from the origin, from x equals 0, starting from right here. And then the object moves with varying speed from 0 to the positive x direction, to the right. Now, let's say that I know that at this point, which I will say x equals 1, the object is here when the time is 1 second. Okay, I'm choosing simple numbers to illustrate the idea, the meaning behind instantaneous and average velocity. And let's say that I have another point right here, which is x equals 1.1, and the moment that the object is here is t equals 1.1 seconds. Now let's say that I also know that the object that is moving to the right, let's say this is approximately, let's say this is x equals 3, and all of these are in meters. So whenever you see x, it's in meters. Whenever you see time, is in seconds. Let's say that the object is at x equals 3 when the time is 5 seconds. Okay, now let's see, if I want to calculate the instantaneous velocity, for example, then I need to find a delta t that is small. Now in this case, for this phenomenon, we start from t equals 0 and we go all the way to t equals 5. What would be a small delta t? I see an example here. I have t equals 1 second, I'm right here. T equals 1.1 second, I'm right here. For the entire duration of the phenomenon, this time difference, the 0.1 second, is relatively small number. So I could calculate the instantaneous velocity right there, delta x divided by delta t, and to find delta x, I have x final, the final position in that time interval, minus x initial divided by the change in time. And in this case, I have a final of 1.1 meters. The initial is 1 meter. So I have a change in x equal to 0.1 meter. And I have a change in time. I went from 1 second to 1.1 second. I have 0.1 second. So my instantaneous velocity in this case is estimated to be about 1 meter per second. Now note that this instantaneous velocity is valid only for this time interval, right? I found the instantaneous velocity, I estimated, I should say, the instantaneous velocity only for this time interval. Now for this phenomenon from t equals 0 to t equals 5 seconds, I can also estimate an average velocity, again using the same expression, delta x over delta t, with now the difference being I'm going to choose a relatively large change in time. So I'm gonna go, I could go, for example, from 0 to 3. So I still have x final minus x initial, and I have the same for time, t final minus t initial. My change in x now, x final is 3 meters, x initial is 0, so this ended up being 3. The change in time is 5 seconds, t initial is 0, so I have a 5, and these are meters per second. Now this is my average velocity from t equals 0 to t equals 5. Note the difference. The instantaneous velocity I estimated to be 1 meter per second. The average velocity for the phenomenon was 3/5 meters per second, which is less than 1. So this is telling me that there were times during this motion that I had an instantaneous velocity more than 3/5. Sometimes the velocity was less than 3/5, but on average the velocity from 0 to 3 meters was 3/5 meters per second.